You're watching ArgMin, lecture series on real analysis, lecture 16, compactness properties and Cantor's intersection theorem. So last class we looked at what it meant to be compact, and A subset of Rn is compact if every sequence in A has a subsequence which converges itself in A. And we looked at the Heine-Borel theorem, which says if a subset of Rm is compact, then A is if and only if A is closed and bounded, and then we looked at this direction and proved it. We won't actually be proving on the other direction of this proof of Heine-Borel. The closed and bounded implies compactness, but we'll just take that for granted and move on with other topics. So here's another lemma we'll be looking at. If A is a subset of B is a subset of Rn, such that A is closed and B is compact, then A itself is compact. So proof. Let's make a sequence contained in A. Then that sequence is also in B, and B is compact. So there's a subsequence AKL which goes to A in B. Since AKL itself is contained in A, and A is closed, then we have that A itself is in A. So set A is compact. So we use Heine-Borel here by by creating the subsequence which converges. So we've now proven that if a closed set is like A is a subset of a compact set, then that closed set must itself be compact. Okay, another thing we'll look at, that Cartesian products of compact sets are themselves compact. We'll just look at the binary case where there's only two of them. Compact. Then A cross B, that's a Cartesian product, which is AB such that A in A, B in B. So that's just another set. Is compact. And proof that there be a sequence of AK BK pairs in A plus B, then AK is contained in A, and A is compact. So we can make a sequence, a subsequence AKL in A such that the subsequence converges in A. Now let's look at the tuples when you use this subsequence, so AKL and BKL, and that's in A, B, since B is compact, the sequence, which is the subsequence of BKLs, has a convergent subsequence. B, K, L, M, yeah, crazy, there's lots of indices there, and that converges to B. So we now have a subsequence using Heineberl on each axis or each coordinate. So finally, we'll just write A Cartesian product with B is compact. Okay. As a corollary to that, if you have n subsets of Rn, then their Cartesian products, or sorry, that's supposed to be of R, and their Cartesian product will be a subset of Rn, and it will be compact if you just use induction on the previous property. And as another corollary, if AB in Rn A less than or equal to B, then the cube ABN is compact, and it'll look like a cube in n dimensions. So if that's not clear what that is, it's just if you Cartesian product AB with itself n times. Oops, there. Okay. Now, let's look at Heineberl again, which we stated as if A subset of Rn, then A is compact if and only if A is closed and bounded. We're going to finally prove it. So the forward direction was in last lecture, and this lecture we're going to prove the backward direction. So closed and bounded implies compact. So suppose A is closed and bounded. Since A is bounded, there must be an m greater than 0, such that A is contained in this cube. To the n. Since A is closed and this is compact, A itself must be compact by the previous lemmas. So proving those last lemmas made this a quite simple proof. So now we know if A is a subset of Rn, it's compact if and only if it's closed and bounded. There's another theorem. is Cantor's intersection theorem. Cantor is one of those mathematicians that managed to get his name on something. Its statement is as follows. If A1 is superset of A2 and so on, this should look like the nested interval theorem. It's a chain of non-empty, compact subsets of Rn. Then if you take their infinite intersection, then that's wrong. Infinite intersection is not empty. And proof. Just recall first, unions of intervals are also compact in R. Okay, so suppose we have these containments. Where each AI is compact. Now take an element from each AK for all K in natural numbers. So that gives us a sequence if we list them out. Since A1 is compact, there must be a subsequence which goes to A in A1. Now note that AKL is in AM for all what is it? K M greater than M, or all M for all KL greater than, that's really messy, KL greater than or equal to M, and that's because a set in AM is in all the ones that came before. Okay, since each AI is closed, A must be in AI for all I in the natural numbers. So A in the intersection of AKs implies, let's just write it this way, is not empty. Okay. So now we've looked at real numbers and we've been looking at real vectors for a while. Now we're going to move on to the next major topic, just a brief introduction on functions. So this is going to be all on limits, functions, and continuity. And first, we're going to talk about limits and continuity. So definition, let F be a mapping from R to A to Rm, where A is a subset of Rn. Let A and A, you take away that set A in the closure. So we can get arbitrarily close to A. We say V in Rm is the limit of F at A if for all epsilon greater than 0 there exists a delta greater than 0 such that 0 less than x minus A less than delta 0 less than delta for all x in A implies that the difference in fx and v is less than epsilon. So what this is saying is as x and A get close, then f of x and v get close. For an intuitive sort of way to write it, but here's a precise way. So it's an epsilon delta sort of situation. What is it saying? So for any epsilon, you can, and for any A, you can give me a delta such that whenever there's another x which is in A, which is close to A, which has distance at most delta from A, then the function has the most epsilon distance from V. And we write that as lim x A of fx equals V. So you would have seen it from calculus before, but here's a more formal way to define it. The limit. Now here's a definition. Another one. So as before, we have this f. We say f is continuous at A in A if for all epsilon greater than 0 there is some delta greater than 0 such that x minus A less than delta for x is in A implies that f of x minus f of A less than epsilon. So this doesn't necessarily mean f of x equals f of A, or the limit as x goes to A of fx is equal to fa. So here's an example of that. Let me highlight the previous definition first. So let A be from 0 to 1 with 2. F maps from A to R and fx equals 3. Let epsilon greater than 0 be given and choose delta equals epsilon. Then if x minus 2 is less than delta, then f of x minus f of 2 is equal to 3 minus 3 equals 0 is less than epsilon. So we can say that f is continuous at a equals 2, but if you try to take the limit as x approaches 2 of fx, it does not exist. So this isn't the same definition as calculus. So just to make it clear, not the same definition as usually seen. So I'm assuming like you took something like an AP Calc or Calculus 1 at your university. In Calc, so the limit doesn't have to exist for it to be continuous at that point. Just add some more words here in a way that you can actually read them, because 2 isn't in the closure, so you can't actually take a limit there. And that's it for this lecture.